Hello class, in this video we'll be covering thermochemical equations, how to interpret them, and how changing the thermochemical equation affects the change in enthalpy of a reaction. Thermochemical equations are defined as chemical equations that also contain information about the enthalpy changes that occur during a reaction. Because it tells us the amount of energy absorbed or released by the reaction, we should be able to identify whether it is exothermic or endothermic based on the value. Just a reminder that the units for the change in enthalpy is usually in kilojoules per mole. An example of a thermochemical equation is shown below along with the enthalpy change or the heat of formation for water. Based on the delta H value, we know that this is going to be an exothermic reaction and that 572 kilojoules of heat energy will be released per mole of a reaction. Another way to say this would be that 572 kilojoules of energy is released when 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to produce 2 moles of water. Because the amount of heat energy released or absorbed by a reaction depends on the amount of reactants, the coefficients or the stoichiometric amounts will affect the value of delta H. If we multiply the thermochemical equation by a certain number, we must also multiply delta H by the same factor. For example, this current equation shows that when 2 moles of hydrogen gas is involved, this will release 572 kilojoules of energy. However, if we were to multiply the coefficients by 0.5, this would now be the new chemical equation. Because this equation now involves 1 mole of hydrogen gas rather than 2 moles, you'd expect that the heat release for 1 mole of hydrogen gas to be half of 572. Hence, if we multiply delta H by 0.5, the heat release for 1 mole of hydrogen gas will be equal to 286 kilojoules per mole. The main take-home message of this slide is to always apply the same changes to delta H if you're multiplying or dividing their coefficients in a chemical equation. Whenever we write a thermochemical equation, it is important for us to always express the physical states of each species. We can write thermochemical equations to indicate both physical and chemical processes. In the example below, I've got the thermochemical equation that shows the physical change when ice melts. If I didn't include the physical states in my thermochemical equation, you wouldn't be able to tell whether this was a physical change from the solid to liquid state or from the liquid state to the gaseous state, thus reinforcing the necessity to include physical states when writing thermochemical equations. In the second example, this is a thermochemical equation for the combustion of methane. In a future video, we will learn how to write thermochemical equations and find the heat of combustion for a particular chemical reaction. We can also write the thermochemical equation for the reverse reaction as well. When we reverse a reaction, we'll leave the value of the change in enthalpy the same, but we need to flip the sign. Let's look at an example down below. In the forwards reaction, A is converted into B, and this is an endothermic process which absorbs 100 kilojoules from the surroundings as shown in the energy profile diagram. If the reverse reaction was to occur, meaning B was turned into A again, the reverse reaction will be exothermic and the change in enthalpy would now be negative 100 kilojoules per mole. As you can see in the forwards and backwards reaction, delta H values remain the same, but the sign has changed. I would now like you to apply what you've learned in the next question. The chemical equation for the decomposition of water is given to you, and the question wants you to find the enthalpy change for the formation of 2 moles of liquid water. Pause this video now, and when you've got the answer, play again to check your solutions. This question wants us to find the enthalpy change for the formation of 2 moles of liquid water. This can be represented as the reverse reaction, whereas the decomposition is represented as the forwards reaction. Because we are reversing the reaction, this means we will need to flip the sign for delta H. Hence, the enthalpy change for the formation of water is equal to negative 571.8 kilojoules per mole, indicating that this is an exothermic process. Because it's exothermic, we can eliminate options C and D. Based on our thermochemical equation, this can be interpreted that the formation of 2 moles of water releases 571.8 kilojoules, hence A is going to be the correct answer. Let's look at a slightly more complex example. In this example, it gives us the thermochemical equation when iron reacts with oxygen, which is an exothermic process. The question ultimately wants us to find the delta H value for the following reaction. If we examine the thermochemical equation carefully, you should be able to pick up that there are 2 modifications made. Firstly, this reaction has been reversed, hence we need to flip the delta H value. As a result, the delta H value of this reverse reaction should be equal to positive 1121 kilojoules per mole. Secondly, the mole ratios have also been doubled. Doubling the coefficients also doubles the amount of energy absorbed. If we multiply 2 with positive 1121, this will give us a delta H value equal to positive 2242 kilojoules per mole. I would now like you to gain further practice by answering two similar questions. Pause this video now so you can attempt to find the delta H value for the following chemical equation. Based on the equation, we can see that the reaction has been reversed. Reversing the reaction flips the sign of delta H, making it negative 49 kilojoules for the reverse reaction. Furthermore, we could also see that the coefficients in the equation have also been multiplied by 3. Multiplying 3 with negative 49 will give us an answer of negative 147 kilojoules per mole. Have a go with the second question. Pause the video now and then play again once you're ready to compare your answer. In this particular reaction over here, we can see that this is the reverse reaction, so therefore the delta H value is going to be equal to positive 1364 kilojoules. You should also have noticed that the coefficients in this particular equation has been multiplied by 2, so therefore I'm also going to multiply the delta H by 2, and therefore this will give us an answer of positive 2728 kilojoules per mole, which corresponds to A. In the next section of this video, we're going to learn how to calculate delta H values from two or more related reactions. Sometimes, questions will ask you to find the enthalpy change for a particular reaction from two or more related thermochemical equations. In these cases, we will need to add the thermochemical equations together to give the overall equation, as well as make a few other modifications along the way, such as multiplying the coefficients or reversing the equation. Previously, we looked at how the delta H values change in response to multiplying and reversing the thermochemical equation, but when we're adding equations together, we need to add the enthalpies of the two reactions together. Let's take a closer look by going through an example. In this reaction, we want to find the enthalpy change for the incomplete combustion of methane in a limited oxygen supply given the following two thermochemical equations. Incomplete combustion is different from complete combustion because it produces carbon monoxide instead of carbon dioxide. To start the question off, we will first write down the balanced chemical equation for the incomplete combustion of methane as shown over here. In this question, our aim is to manipulate these two equations and then finally add them together to result into this reaction over here. If you look carefully, you can see that there's 2 in front of methane, but there's only a 1 in front of the methane provided in the original equation. So the first thing that I'm going to do is I'm going to multiply the first equation by 2. By multiplying the first equation by 2, I also need to multiply its delta H by 2, hence our chemical equation will now become like this. We also need to make another modification to our two equations. As you can see over here, carbon monoxide is a product, whereas it's not a product in the original two equations. So what I'm going to do is I'm going to reverse the second equation so that carbon monoxide is now a product. By reversing the equation, this will also change the sign of the enthalpy, so now it's going to take on a positive value. From here, I can now add the two thermochemical equations together. This means that we add the reactants with the reactants, products with the products, and the two enthalpies together. Hence, we should be able to get this as our answer. From this point onwards, we just need to simplify and cancel things out. Carbon dioxide can be cancelled out because there's equal quantities on each side, and we can also cancel out the oxygens from the products because there's oxygens found on both sides as well. This ultimately gives us the thermochemical equation for the incomplete combustion of methane. These sorts of questions tend to be more challenging, so have a go with answering 2 more questions to get further practice. Pause the video now and give yourself some time to answer the question. Resume the video again once you're ready to check your answer. To arrive to the final answer, we need to manipulate one or both of the thermochemical equations provided and then add them together to give us this equation over here. In the final equation, you should have noticed that the reactant is iodine in the liquid state. Since none of the original equation has iodine in the liquid state, we can accomplish this by reversing the first thermochemical equation. Hence, we need to flip its delta H value, resulting in an answer of negative 16 kilojoules per mole. Therefore, we should be able to get the answer if we added this equation with the second equation and make appropriate simplifications. When we add the two equations together, we can further simplify it by cancelling out solid iodine from both sides of the equation. Adding negative 16 with positive 62 gives us an answer of positive 46 kilojoules per mole, hence C is going to be the correct answer. Have a go with a slightly more challenging question. In this question, you're trying to find out what is the enthalpy change for this equation over here given these two thermochemical equations. The first thing that I'm going to do is I'm going to reverse the first reaction because I want sulfur dioxide as a product. If I'm going to reverse the first equation, I'm going to need to flip the sign of the delta H value, so therefore it's going to be positive 196 kilojoules in the reverse direction. From this point onwards, what I'm going to do now is I'm going to add these two equations together. By adding these two equations, you should be able to get this as an answer, and then you should be able to cancel out the SO3s from both sides of the equation as well as oxygen as well. Your simplified equation should now look like this. Now, we've almost arrived to the final answer. However, in this particular equation over here, the coefficients for each of these species is 1. So what we're going to be doing is we're going to multiply each of our coefficients by 0.5 as well as our delta H value. In doing so, this is going to be our final answer. By now, you should be able to meet the success criteria in this video. Thank you for watching, and I'll see you guys again in the next one. Bye.